Uh, I'm Richard Crisp, and let me just get on with it. So today I'm going to fly over my upcoming class that'll be on the 20th of August, and I'm going to try to cover a little bit of each of these 8 sections. So let me just get on with it now. Let's start out with image sensors. The first thing we need to do is to be able to capture an image. And to do that with a semiconductor, we're going to exploit the photoelectric effect, which, by the way, was the subject of Einstein's Nobel Prize in 1921. And basically, if you shine a light on a semiconductor, you liberate electrons from it. And so in the case of something like silicon, as we turn the light on, we see an increase in the concentration of minority carriers. And so that's how we're going to create the charge carriers. So we're going to convert photons into charge carriers in a semiconductor substrate. But then we need to confine them to regions that we'll think of as pixels. And then we need to find a way to manipulate them and move them around so that we can measure how many there are. When we're exposing light to the semiconductor, depending on the wavelength of the light, will determine just how many charge carriers we end up liberating per photon. And so within the visible light region, we get essentially 1 electron for every interacting photon. So that is a nice convenient number. At higher energies or shorter wavelengths, you actually get a higher quantum yield than 1, and you can compute what that is by taking the energy of the photon and dividing it by 3.65 electron volts per electron, and that'll tell you how many electrons you yield in that. But we're going to focus on visible light. So once we've created the charge carriers, we kind of like to be able to confine them into pixels. So over on the right-hand side, you see a cross-section of a CCD-like structure where the blue rectangles represent gate electrodes that we can connect to different voltages. And then there's a gate oxide, so we sort of form a capacitor with that and the silicon substrate, which is over on the right-hand side. And by applying a bias voltage, we'll create a space charge region that's depleted with majority carriers, and in fact have a potential well where electrons can be gathered up. And if we change the voltage that's on the gate electrodes, then we can move the position of that potential well, and in so doing, move the charge carriers along with it, as if it was on sort of like a conveyor belt or what have you. In some sense, you could sort of think of the electrons being caught in a potential well as being very similar to planets that are confined in gravitationally warped space, as I've shown down at the bottom picture. And then over on the left-hand side, this is a simulation of a pixel of a backside illuminated device. And you can see the blue cross-hatched region represents the potential, and the physical X and Y dimensions are shown as well. We're not showing the Z dimension, so don't think of the potential as a Z dimension. I've also tried to represent the gate electrodes. So I've tried to make this be essentially the same as what we have on the right-hand side, but now sort of an isometric view. And so you can see there's a little pocket that the electrons fall into, and as we vary the voltage on the gate electrodes, we'll move that pocket around. Okay, so let's talk about, now that we figured out how to generate charge carriers from the light, and we found that there's a way that we can confine those charge carriers to regions that are useful. Now let's talk about how we build an image sensor out of that. So there's a few key functions on a charge coupled device, a CCD, and that's what I'm going to discuss first. I'm bringing that up because that was sort of the original solid state image sensor, and it's easy to understand how they operate, and a lot of the same principles behind the CCD are used in CMOS image sensors, which essentially dominate the business today. But we'll start out with CCDs. So sort of the first thing that we need to do is the charge generation, and I've just talked about that. It's the photoelectric effect. and it does light to charge conversion. The next task is charge collection. So I've talked about forming a potential well by having these gate electrodes that we can selectively bias to create potential wells. And those will allow us to create discrete regions so we can capture the charge in pixels in an XY array. And then the next thing that we need to do is we need to transfer the charge to a place where it can be conveniently measured. And in a CCD, that could actually be a few inches. A lot of those are fairly large image sensors. In a typical CMOS image sensors, the transfer distance is a very short distance. I'll probably touch on that briefly as we get into the slide deck. So once we've moved them to where they can be measured, the next task is to measure them. And to do that, we put the charge on a sense capacitor, and then we essentially measure the voltage on that capacitor using an analog to digital converter. So that's how we make an image sensor. So let me get further into it. This shows a picture of a kind of a schematic diagram, if you will, of a 3.2 megapixel image sensor over on the left-hand side, a CCD. And over on the right, we see kind of a schematic representation of how this works. So if you can imagine the photons falling into some little collection buckets that are mounted to a conveyor belt, then we can allow everything to stand still for a little while and allow the raindrops to gather, the photons, in other words, into the little buckets for some period of time. And then we can start to dump the buckets kind of one row at a time into a second set of buckets on a second conveyor belt that would consist of what we call the horizontal register. So looking over on the left-hand side, the usual or the usable active area, the CCD array, is represented by that first conveyor belt. And then that thing that says 2184 active pixels per line, that represents the horizontal conveyor belt. That's called the horizontal shift register. So essentially what we do is we click down the big conveyor belt on the top that captures the raindrops. We click that down one index point, then we dump out each one of those buckets that are on the horizontal register, and then we measure as we do that one at a time, and that's how we get the entire image out of the image sensor. As you can imagine, this takes some time because it's essentially one pixel at a time that's read out, and that's one of the key disadvantages in CCDs, is the inherently serial readout function. You can also imagine that if maybe one of those buckets had a hole in it, especially in the horizontal register, that essentially everything that we dumped in there might get leaked out. And so they can be very vulnerable to damage from cosmic rays and other sorts of things. And that can actually trash an otherwise good image sensor. So there's some well-noted disadvantages of CCDs. So now let's talk about CMOS image sensors. They still have the same task to go through about generating charge, collecting charge, transferring it, measuring it. But then we can actually do one more function just by the nature of CMOS circuitry, and that's we can build good A to D converters, and all the downstream signal processing circuitry can actually be integrated onto the image sensor itself. It's just simply not practical to do it in a CCD because they're generally all one polarity of transistors. So it's either an N channel or a P channel type array. And so there's not both P-type transistors and N-type transistors. There's generally only one flavor of transistor. So as a general rule, the analog to a digital conversion step is done off-chip in a CCD and requires a fairly substantial amount of electronics to support the image sensor. Whereas with a CMOS image sensor, it can all be done on chip. There's some other important differences as well. And a key one is the operation of the shutter in the CMOS image sensor. The most basic CMOS image sensor essentially exposes and reads out a line at a time. Actually exposes all the lines, but it it kind of reads out a line at a time. And an issue arises if you have motion in the image, because if you look over here at the bottom left-hand side, you see these striped colored bars. Those represent an image line, and you see that their beginning and end times are slightly offset. And if you look at the timing diagram, during that offset time is when we're actually reading out one of those lines and making an electronic signal out of it. So the start and stop times are different on each line with this so-called rolling shutter, which, as I said earlier, was the simplest CMOS image sensor. And so long as you're taking still images, this causes no problem at all. But if you have high-speed motion, or you have motion within the image frame while you're taking it, like video, for example, or particularly video of sports or something with high action in it, you can get some strange distortions. And so this is an example of the type of distortion that you get. You see the bus, instead of being straight up and down right angles on it, the top actually was imaged at a time different than the bottom, and the bus has moved a little bit. So you get this sort of curved effect. And so that's a rolling shutter artifact. And for those of us that fiddle around with this kind of stuff on a professional basis, it's always fun to, watch something on television, an airplane, a propeller, or something like that, and say, oh yeah, they used a CMOS rolling shutter image sensor for taking that image. It's, to the trained eye, you see it. You can get around that, though, with something called the global snap shutter. And the idea there is to dedicate some quantity of the area of each pixel to be essentially a storage capacitor, and to have a transfer gate within the pixel that allows us to expose all the pixels at the same time, and then in a single operation to transfer that charge from the photodiode that's catching it, that's exposed to the light, to a light shielded portion of the image sensor where that charge can be stored, just a bulk transfer. And then once it's stored in that light shielded region, then we can go and read the lines out one at a time without having that distortion. But as you can imagine, you've got to now dynamically store charge for a different amount of time in each pixel row. So at the top, it would be stored only for a very short amount of time, and the charge at the very bottom of the sensor would be stored for a longer period of time. And depending on things like operating temperature and how strong the signal is and so forth, you could see some noise differences in the image from top to bottom. But the thing that it does that's really good is it corrects that rolling shutter focal plane distortion largely. And so you see that at the bottom, these two images taken of an electric fan. With the rolling shutter, which is denoted A in the image, you see a very peculiar looking arrangement of the fan blades. And on B, that's the snap shutter. There's still some distortion, but it's not nearly as bad as what you get with the rolling shutter. Okay, so the next thing I want to talk about is noise. That's a big deal when it comes to image quality. And so sort of the first and maybe most basic noise that we need to understand is shot noise. And these are essentially photon statistics. Incident photons have a Poisson arrangement in terms of the numbers at a particular time that are collected. And when you sample a Poisson type arrangement like that, you get an RMS noise, and that's equal numerically to the square root of the number of photons. So this would just be light that's shining, visible light that's shining. Now, if you talk about, there's a shot noise of the photons that actually interact with the silicon. Not all of that incident light will interact with the silicon, but of that does, you have a shot noise associated with that also is equal to the square root of the number of incident photons. I think I failed to say that initially about the Poisson relationship, but that value is equal numerically to the square root of it. Now, not every photon that interacts with the excuse me, not every photon that hits the silicon interacts with it, but those that do yield a whole electron pair. And for visible light in silicon, that quantum yield n sub I is equal to 1. So numerically, the shot noise associated in electron units associated with an incident photon would be n sub I times the square root of the number of incident photons, which if you work through the math, just reduces down to the signal as measured in electrons divided by the I'm sorry, it would be equal to the square root of the signal in electrons times the quantum yield, but the quantum yield is equal to 1. So you just get a simple equation of S, which is the signal in electrons to the 1/2 power. So that's the best you can ever do with a single image frame in terms of noise, is to reduce it down to the shot noise. So when we go to process an image, our goal will be to make sure that it winds up being shot noise limited after we do various calibration functions. So read noise is another important noise that we deal with in electronic images, and it really represents the uncertainty in measuring the pixel charge. And so if you had no light at all shining on the image sensor and you just read it out, the noise in that image frame would be the read noise. And interestingly enough, the generation of the charge, the collection of it, the transfer can actually be noiseless processes. But the signal, but the read noise, comes from an amplifier, and that is going to have, it'll be the place where you're going to see noise being injected in. And you can't really do much about the read noise other than to take multiple images and combine them together to reduce it, or to take an image that has a very large amount of signal compared to the read noise such that the read noise is insignificant. So that can be an exposure parameter optimization. Fixed pattern noise is another noise source that you see in images from real image sensors. And there's a couple of different types of it. The key one, the FPN of the image sensor itself, is caused by variation of the gain from pixel to pixel. But you can also have, I would call it illumination or optical type fixed pattern noise, and that's caused by non-uniform illumination. Most commonly, it would have to do with the light intensity roll-off from the optical system. For conventional lenses, as you go off axis, the intensity of the light rolls off like the cosine to the 4th power of the chief ray angle. Also, you can have dust on the optics, and in particular, most of these image sensors, particularly the scientific CCD, are monochrome, or many of them are monochrome. And so in order to get color images, they'll use filters in front of the pixels. And so it's possible to have dust motes on the filters and on the optics and on the optical window. And that'll create artifacts that can be visible on the image. And that's another form of fixed pattern noise. One of the challenges with fixed pattern noise is that it's proportional to the signal level. So simply taking a longer exposure doesn't get rid of it. And so if you're in the operating regime of the image sensor where you're fixed pattern noise limited, you don't see any improvement in the signal to noise ratio by increasing the signal level. But it turns out that there's some rather straightforward things that we can do to actually remove the fixed pattern noise within the limits. And one of those is to perform something called a flat fielding operation. And essentially what you do with flat fielding is you create a calibration image, which would be an image of a plain uniform background that should be a featureless image. But any feature you see in the image is actually the fixed pattern noise of the image. So if you have a good flat field image, then you can divide that into your real image pixel by pixel and eliminate the fixed pattern noise that way. I also mentioned the optical intensity roll-off. Since that can be algorithmically corrected just by making a lens model, a lot of times you'll see, particularly with CMOS image sensors that have an on-chip signal processor, you'll see some built-in functions of doing lens shading correction, as they'll call it. And that can compensate for the intensity variation from the center of the lens to the edges of it. So those are the key things with fixed pattern noise. There's another kind of nasty noise, and that's related to thermal dark current. With no signal at all applied or no light applied to the device, but letting it integrate in the dark, you will actually accumulate some charge in the pixels. And that's due to thermal generation of charge carriers. And this diagram shows how, kind of schematically, how places where you can have thermally created noise. One of them is just whole electron pairs that are created thermally, and they can hop from the valence band to the conduction band. But also in the near the surfaces, you can have trapping sites and other states that can hold charge that will behave with thermal sensitivity. So when they're hot, they don't stay trapped very long. When they're cold, they'll stay trapped a lot longer. So all of those things can contribute to thermal dark current. And thermal dark current actually has a couple of different manifestations. One of them is a shot noise. So in the same way that we had photon shot noise associated with the Poisson distribution of the light, we also have a dark current shot noise. Once the electrons are caught within the pixel, all electrons look the same. They could be generated by the light, or they could be thermally generated, or they could just be something that's left over from a previous exposure. The image sensor doesn't really care. So it's very important to minimize this dark shot noise because it'll degrade the signal to noise ratio of the image. And I'll show you in a future slide here just how badly it can degrade it. And it's really a problem as you start exposing for longer exposures, like you might do for scientific type applications. There's also non-uniform distribution of the thermally generated charge carriers. As I mentioned, you can have defects in the crystal lattice and so forth, and those don't change. So in those regions, you'll get higher dark current than you do in other regions. And so because things don't change with the dark current fixed pattern noise, you can actually correct that. And so you can correct that by subtracting a dark image taken under the same exposure conditions as your light on image. You just subtract it. So you take an equal length dark exposure operating at the same temperature and subtract that from it. And then there's this thing we call the D sub n, or dark current FPN factor. And that's a datasheet parameter that you can look up on a lot of image sensor data sheets. But if you can't look it up, then you can actually measure it. And I'll talk briefly about how we can do that a little bit later on. But at any rate, what that is it's a constant that we can multiply times time, and that'll tell us how much dark signal that we get. Okay, so here's an example of a raw image that's been degraded by dark signal non-uniformity. So that we see the raw image over on the left-hand side, that's a 2-minute exposure. And by just simply subtracting a dark frame from it that was exposed the same way, but with no light, you can see that it significantly cleans up the image signal. So that's an example of how despiking can do a tremendously good job of improving your signal to noise ratio. And this is very commonly done in things like scientific imaging, in particular astronomical imaging. They take long exposures. Sometimes some of the biofluorescence type applications will take multi-hour exposures as well. And so this is very commonly done to those. Okay, so the next thing we'll talk about is how can we actually characterize the performance of a camera and the image sensor. So in order to be able to correct it or to improve it or to gauge the quality of the image, we'd like to have an objective measure to assess the performance. And so there's a technique that was developed at the Jet Propulsion Laboratory starting in the early 1970s by my friend Jim Janicek called photon transfer. And there's a whole book written about it that's published by the SPIE press. And there's sort of two major categories of photon transfer. One of them is using non-calibrated light, and you're essentially looking at noise versus signal. And then there's another variant of it that's called lux transfer. And that's where you use calibrated light source and you're actually looking at signal to noise versus the absolute light level. I'm going to focus primarily on the photon transfer, the non-calibrated light source in the next few slides. So the idea behind photon transfer plots is to decompose the image into different types of products that we're going to plot graphically. And to do that, we'll take two identical images and we'll do a frame subtraction. Typically, you'll add an offset to one of the frames so you don't deal with any negative numbers and you don't want to clip the histograms. But we'll take that difference frame and we're going to make some measurements on it. And so what we do is we take a sequence of these exposures starting from no signal, and we can measure read noise that way, all the way up to saturated image sensors. And so we may take 50 pairs of exposures, or we might take 20 or whatever, but take a number of these as you vary the signal intensity. And as you plot out the noise on a log plot, you're going to go through several orders of magnitude. As you do that, you'll get this curve like shown in the middle, and that'll actually show you a plot of your noise as a function of signal logarithmically. And it turns out that there's 4 different regimes of operation in here that you can see from the slope of the noise line. So over on the left-hand side, the read noise limited regime, the slope's going to be equal to 0. And the intercept on the y-axis would actually be the read noise. So that's a simple way to measure the read noise. The next regime that you see, we actually see a slope of 1/2. And that corresponds to the shot noise. Remember, I said it equaled the amount of signal to the 1/2 power. And if we draw a extrapolation of that back to the x-axis, where the signal crosses the x-axis is actually the gain constant. It tells you how many ADU units do you get as a function of each electron, for example. And then the next region where the slope has kicked up to be a slope of 1, that's the fixed pattern noise limited regime. It's very common for the fixed pattern noise limited regime to actually occupy most of the dynamic range of the image sensor. And with if we take that slope equals 1 line and we extrapolate that back to the x-axis, the crossing point is actually equal to 1 over this FPN factor, or P sub n as I call it on this particular plot. And that's the number that tells you for any given amount of signal how much noise is fixed pattern noise. And so that's a convenient way to measure that. So you get to measure a lot of these different performance related parameters like read noise, the conversion gain, the fixed pattern noise. And then as you go all the way over to the far right, eventually you reach full well or saturation. And of course, when it's completely saturated, all the pixels have the same value. So naturally the noise drops off. But this allows you to very accurately measure the saturation level of the image sensor. So you can do all of that without a calibrated light source. Now you can do the same thing, but in the dark, and you can get the dark transfer plot. And so that'll allow you to know what the conversion gain is going to be the same, but it'll tell you what the dark fixed pattern noise factor is as well. So those are, that's a very, very handy tool. I've used it a lot in characterizing cameras and image sensors. The next area that I'm going to talk about is image sensor manufacturing. And the key things here are the wafer fab process, and then creating backside illumination devices, and then looking at some new ideas about die stacking. So the key thing in the wafer fab process is the starting material that we use in the wafer fab. We want to use something different than is used for memory or processors. And what you want are high resistivity wafers or epitaxial layer on it. And the reason for that is you want deep depletion regions. And I don't think that I have material to talk about the depletion regions and so forth, but I'll get into that in the regular class. There's another issue, which is the photolithography. A lot of times image sensors physically are very large. And with modern photolithography tools, the steppers, they actually have a maximum exposure that they can make, maximum size exposure. And that oftentimes is smaller than the size of the image sensor you might like to make. So if that's the case that you're dealing with, then we do things called stitch reticles. So if you have a 2x2 stitch reticle in a 20 mask process, you would make 40 masks. So one of them would be half of the die and the other would be the other half of the die, and they get exposed multiple times on each layer. The other thing is in the wafer fab process is, as I said, we want deep depletion regions. So the doping profiles are quite different than you'd have for logic type devices. And also we generally do not need ultra small transistors like you'd like to have in a processor or memory device. And for copper, I mean, for CMOS image sensors in particular, it's nice to have copper metallization versus aluminum because we actually have current running through the image sensor array. And that kind of means that you got to be a 65 nanometer node or finer geometry. These are kind of detailed manufacturing issues. In order to get really good small pixel performance and so forth, the backside illumination is increasingly used, and the manufacturing implication of that is you have to thin the wafers to be something like 10 to 20 microns thick, and develop, and where you've cleaved the backside where the light's going to shine in, you want to passivate that by putting an accumulation layer so you don't create a bunch of trapping sites for the generated charge. And then in some of the newer architectures, they're actually doing die-on-die stacking, and that's a pretty exciting development in recent years. And one of the key things you might like to do on that is to have the one layer of or one die that's stacked on top of another die that's nothing but photodiodes and optimized for charge or light to photon, light to charge conversion. And then a layer below that may be more optimized like a logic device for reading out and processing the image data. The other thing that's interesting for that is that if you wanted to do things like non-optical or non-visible light sensing, like shortwave IR, for example, you can use a different type of semiconductor and use a compound semiconductor for sensing the light, and then still use ordinary silicon CMOS for the other tasks. And I've seen an example of an interesting image sensor architecture developed by Sony, where they included a DRAM memory in the stack. And the idea from that is they can take a very, very high frame rate to get a decent slow motion. And of course, the number of frames is limited by the storage of the DRAM. But the idea is to take a few seconds of very high frame rate video for certain kinds of sports photography and other things like that. Just to give you an idea of the difference in the lithography, in the older days, over on the right hand or the left hand side, you see a 4-inch wafer and you see a bunch of different image sensors on it, and that's possible with that type of photolithography because when they do the masking, the entire wafer is exposed with a single flash. With a stepper, though, they actually step and repeat the reticle across the wafer. So you can't really easily put different designs on the same wafer like you could in the projection printer days. I mentioned the task of making small pixels and doing backside illumination. This describes or shows the problem that we try to solve by doing that. You can have some real challenges with tiny pixels getting the light down to the photodiode with CMOS image sensors. They have 2 or 3 or maybe even 4 wiring layers of metal on the top, and that creates sort of an optical tunnel, if you will. And it can be really, really difficult, particularly for the image sensors that are the pixels that are off axis pretty far on the image sensor. It can create problems getting the light down to the pixel. And then on very, very sharp, very fast lenses with a steep chief ray angle, you can actually get optical crosstalk where light that should be maybe under the red filter ends up getting sensed by the green pixels. So that can be also improved by having backside illumination. So briefly, what they do with backside illumination is to, the left-hand side shows a front-side illuminated device. These features you see in the middle are metal lines running through it. Down hit this bottom line is where the actual image sensor occurs, the photodiodes and so forth. So this is where you need to get the light. And what they do with backside illumination is they flip it around backwards and they grind off most of the silicon. So now all the metallization and other structure that's above the surface of the silicon is not exposed to light. And what is exposed to light is the region where the light's going to be captured. And then, of course, they put micro lenses and so forth in there to focus the light directly in the region. So that avoids the optical tunnel problem. It supports faster numerical apertures, like faster F numbers, and it can help deal with the crosstalk. So the next thing I'm going to do and talk about basically for the remainder of the talk is camera design considerations. So,
hi, Richard. This is Laura. I'm sorry to interrupt. I just wanted to give you a time check and let you know we have about 20 minutes left in the presentation. So if you wanted to do a little bit of Q, maybe another 5 minutes left or so.
Yeah. Okay. So what I'll do is I'll use the next 5 to 7 minutes, and I think I can get through the rest of these pretty quickly. But the first thing you want to look at is how bright's your target in the background. And so if it's a really dim target, you want to have long exposures, and that's going to mean cooled sensors typically. So I'm not going to spend a lot of time on this, but I spent a lot of time on it in the class. And then if you're shooting video, if you need a full frame CCD, you've either got to have a pulse light source or a mechanical shutter. CMOS though, you have an electronic shutter. You can have rolling shutters, or you can have the snap shutter as well if you have motion in the image. Finally, one of the things that we care about is the optical characteristics. So it turns out that light doesn't focus to a point. It actually focuses to what they call the diffraction limit. And when you focus the light, you see this profile, if you will, of the light focus cone. And there's something called the Airy disk, which is how small it will focus down at the bottom. And that's a function of the the F number of the lens that's exposing it. And you can control the diameter of that Airy disk by varying the focal ratio of the lens. And then the trick is, how big do you want to make the optical spot as a function of the pixel diameter? And without going through the math in this, let me just say that if your pixel size is 4.88 times, or 1 over 4.88 times the diameter of the Airy disk, then you'll be at exact Nyquist sampling of the optical blur. So that's what you should strive to do if you can do that. So the last portion of this thing is going to be really talking about cost factors and some of the design considerations. Shutters can add a lot of cost to an image sensor or to a camera. And there's different kinds of shutters: an iris, a curtain, or a rotating disc. Also, the imaging optics are a very costly aspect of the camera typically. And if you've got to have cooling built into it, then you've got to deal with thermal management and a environmentally sealed camera housing. And then if you've got high resolution and high frame rate, you're going to have high camera bandwidth. And so the electronics that have to support high frequency data transmission cost more than those that support low frequency. So let's talk some about camera design now. The basic problem is you want to take a video, including with objects moving in the video frame. You might want to identify objects. You're worried about image blur, image distortion. How do you deal with this and engineer a solution? So you start with an instantaneous field of view that's appropriate for the target, and decide how big of a horizontal field of view you want and what the vertical field of view is you'd like. Lens focal length, focal ratio, pixel size, are the objects moving at high speed or whatever? How much distortion can you tolerate top to bottom, and so forth. And so you go through this iterative loop a few times to calculate the basic instantaneous field of view. So that's how much of the field of view does a single pixel see with the optics. You just apply basic trigonometry. And typically you might want to have a 2x2 pixel coverage of the spot, or maybe 4.88, as I said on a previous slide. Then if you're concerned about motion blur and pixel smear, you got the shutter open, the spot's moving. Over how many pixels will you allow it to travel while the shutter's open to smear the image? So you figure that out by determining how many milliradians per pixel is the IFOV, and then how many pixels or milliradians per second is the target traveling that you care about. And then you got to look at the exposure time, and that's usually the main parameter you have to adjust. So there's sort of this iterative process of exposure time, pixel size, and how big the spot is that you go through in order to engineer a solution for that. I think I just said all of that. This says it mathematically, but again, you're just solving a lot of triangles using trigonometry. So now let's talk about designing the camera controllers, and I've only got a few slides left. A lot of times, because of the number of cameras sold is small, typically FPGAs are used for designing a camera controller. And these days, the FPGA suppliers provide a lot of soft IP that can do various tasks that you might want to put together in your camera controller. And so typically you may want to have a interface block that talks to the type of signaling technology your image sensor is using. You may have a processor on board, like a RISC-V processor, to do signal processing for you. You might want to have a neural network. You might want to have an interface to DRAM for a frame buffer. You might have a network interface like Ethernet or USB, and so on. So typically all that stuff is purchasable as IP blocks, and then you essentially design using FPGA design methodology. Now let's go through some specs on a camera. So if we had a 30-bit camera that we want to design that could do 25 frame per second 4K video, how much bandwidth do we need? So what you generally do, because the data rate coming off the image sensor is generally different than the network connection for the camera's data rate, you usually have a frame buffer. So essentially what you do is you store the incoming video in the frame buffer, and then you read it out, and you need to both write it and read it out within a single frame time without losing any pixels and without losing any frames. So for example, on a 4K video, 3840 by 2160, 30-bit, we can calculate the number of bits per pixel at 4K 60, 4K 30 frames per second, and 90 frames per second. And then this will tell you how many megabytes per second that you got to get out of your frame buffer. So this will tell you essentially how fast your memory needs to be, what the clock frequency be. So in this case, for 30 frames per second and 30-bit color and 25 frames per second, we need about 1.55 gigabits or gigabytes per second. And if we had a DDR type memory that's 16 bits wide, that'll transfer 4 bytes per clock cycle. That says we got to have at least a 388 megahertz clock frequency on the memory. Probably use 400 on it. The next task is how many bits do we need in order to store for that? And generally, it's quite a bit less than a gigabit for many of the image frames. For this particular case, 4K video with 30 frames per second, it would be about 1.1 gigabits. But a lot of times, 256 megabits is sufficient. You end up buying a bigger one because you need the bandwidth. And I think that might be my last slide. So I will stop. And open
Thanks
it up
so
for
much,
questions.
Richard, for that fantastic presentation. Clearly, there's so much information that you cover here and that you'll be covering a lot more in detail in your half-day course at Optics and Photonics. So we do have quite a number of questions in the Q&A. So I'm going to read them just because of time constraints. We have about 5 minutes left. So I'm going to go ahead and dive right in. First question is from Faraz Udin Said, and the question is, how do you confine the photon particles in sensors?
Yeah, so you can't really confine the photons other than with the lenses, but by having this array of pixels with biases applied to the image sensor, it essentially creates those little buckets like we saw on the conveyor belt diagram. And that will confine the charge to discrete pixels, even though they're coming in a broad sheet. So in effect, you quantize or divide it up into a bunch of pixels that way. I hope that answered your questions.
Thanks, Richard. We have another one from Alexander Lin. So the comment in the Q&A is the lens shading correction corrects for the relative irradiance fall off from the optical system, and flat fielding can be used to correct for sensor non-uniformity. Is there a way to correct for vignetting?
Well, the vignetting and the optical roll-off are kind of similar. I kind of think of them as really the same thing, but a difference in degree. And good old vignetting, where there's just no light, you're just not going to be able to recover the area where there's no light. And in fact, if you have a lot of light roll off to the point where maybe you've only got 10% of the light intensity that you do in the center of the image, even though you may correct that by flat fielding or by lens shading correction, you'll find that that region of the image is noisier than the other part of the image, because essentially you had a low signal to noise region that you gained up, you applied a bunch of gain to it. And so that's just going to amplify the noise as well. So there's some limits as to how extensive of lens shading you can correct, or how much tolerance you can have of the vignetting. Hope that answered the question.
Thanks, Richard. Another question here. How is the spectral response or the QE curve measured?
Yeah, that's another thing that I talk about in the class. Essentially, you use a calibrated light source and a beam splitter, and you don't have to have a calibrated light source, but you have a light source and you have a way of measuring the intensity of it. Typically, they'll have a calibrated photodiode and then a beam splitter, so that at the same time that you're illuminating the image sensor with this light, you're measuring the intensity of the light. And you, in effect, are using the CCD or image sensor as if it was sort of like a solar cell. And so that's the basic setup as to how the quantum efficiency is measured. And then, of course, the light source, you'd like to have single wavelengths. So that can be done using either filters, or in some cases, they'll use a monochromator, which is sort of like a continuously tunable optical wavelength light source. You could think of it kind of like a signal generator, but it's an optical one.
Thanks, Richard. Let's see, we have a few more minutes here. I have one from Lu Chang asking, do you think the CMOS image sensor will replace the CCD completely in 5 years?
There's some applications where CCDs are just really better, and the high cost and the customization that's frequently needed for those may not be a consideration, because they're put on large telescopes that are publicly funded, like the European Southern Observatory in South America, or maybe any a space telescope kind of a application or whatever. CCDs in space maybe aren't such a great choice, even though they work really, really well because of their sensitivity to radiation damage. I didn't really mention it on the CMOS, but if you get a damaged pixel with CMOS, it generally doesn't take out the whole sensor. You may just have a bad pixel or maybe a bad cluster of pixels. Whereas with a CCD, if you get a damaged pixel in the wrong location, like near the output amplifier and horizontal register, you can't read out the CCD at all. There are some differences in the calibration of a CMOS image sensor. In particular, the flat fielding process has some challenges because of there's a couple of kinds of nonlinearity in the image sensors. There's V over V nonlinearity, and that's something that'll calibrate out nicely using flat field. You can handle that kind of nonlinearity, but V over E nonlinearity, which is essentially the voltage dependence of a reverse bias, the capacitance of a reverse bias junction, that's highly voltage dependent, and over the voltage ranges that the CMOS image sensors operate, you may see a 2-to-1 variation in that capacitance from no signal to saturation signal. And so because of that nonlinearity, the flat fielding process may not be 100% effective at removing FPN. And so in those applications, you may see some resistance to using CMOS, but they could replace it. For most of the commercial applications, CMOS will work well enough that it's being used, but I think in some of the scientific applications, you'll continue to see CCDs.
Thanks, Richard. I think we have time for maybe 1 or 2 more questions here. There's a question here from George Nardov. When would you need a mechanical shutter if you already have an electronic shutter?
Okay, well, if you have a rolling shutter CMOS, for example, and you want to use it with video, I think you could use a mechanical shutter and avoid a lot of those shutter artifacts. But there are times when, if you wanted to take a dark image, for example, for a dark calibration frames, that you'd like to be able to shutter the image sensor. And so the electronic shutters may not completely block all the light and may affect the dark signal as well. But generally, the mechanical shutters are used with CCDs, like full frame CCDs, or perhaps with the frame transfer type. I discuss each of these in the class. There was a architecture of CCD developed called an interline CCD, which does feature a global global snap shutter. And so those are good for video. And in fact, the Mars rovers that drove around on the surface of Mars for much longer than anyone ever expected them to actually used a Kodak interline CCD in those cameras. So those actually work pretty well. But again, if you need to take a dark field image, the light shielding is not perfect on those interlines, so it's good to have a mechanical shutter for those. But generally, you'll see the mechanical shutters used with CCDs, and you'll see the electronic shutters mostly used with the CMOS image sensors.